history of aviation has always been a struggle with the laws of physics. Every mistake in this fight could cost lives. Therefore, today the main tests take place in digital simulators and computational models, and not on real airfields. This reduces risk and speeds up the development process. The aircraft carrier remains the most expensive and at the same time the most vulnerable ship in the fleet. For this reason, he never acts alone. An entire aircraft carrier strike group is formed around it, which is a small naval army concentrated around one ship. A typical group composition includes an aircraft carrier with a deployed air wing. Its deck can accommodate approximately 89 aircraft, providing close strike power. This is the main element on which the effectiveness of the entire group depends. The group is joined by 2 or 3 cruisers or destroyers equipped with the AWACS system. This system is a powerful multifunctional radar and a set of standard interceptor missiles. One such destroyer is capable of simultaneously tracking more than 100 air targets and hitting several of them. In an anti-ballistic missile configuration, the SM-3 missile system is capable of intercepting warheads flying along medium trajectories. In addition, it includes 2 or 3 nuclear submarines. They move underwater, remain invisible, and hunt for enemy submarines that could pose a threat to an aircraft carrier. On board, they are carriers of Tomahawk cruise missiles, intended for attacks on ground targets. To support long-term operations at sea, a supply ship is needed. An aircraft carrier consumes huge amounts of aviation fuel, ammunition, and food. The supply ship allows you to replenish supplies without returning to port, thereby extending the group's combat effectiveness. The group also includes reconnaissance and anti-submarine aircraft based on the air wing. Helicopters perform missions to search for and neutralize enemy submarines. This air component expands the team's range of capabilities. The entire composition occupies a vast ocean area. Destroyers are distributed tens of kilometers from the aircraft carrier. Submarines are even further away, and reconnaissance aircraft fly over even more distant areas. This is not just a cluster of ships, but a 3-dimensional control zone with a radius of several hundred kilometers. Despite its scale and power, vulnerability remains. Therefore, long-range anti-ship missiles, hypersonic warheads, and drone swarms are being developed. Each shield has its own spear, capable of breaking through the defense. The carrier strike group remains the most powerful force projection instrument ever created by mankind. At the same time, it serves as the main goal that developers have been working on for 30 years. 3 parts, 30 blocks, 30 stories about how physics, engineering, and human choice shape the most technologically complex area of military science. Behind every plane, there are thousands of people. Behind each system are years of research, and sometimes lives given for the sake of progress. Behind every decision, there is a compromise between the possible and the desired. At an altitude of about 12,000 meters, air pressure drops to 1/5 of sea level. With such a drop, the oxygen content in the air remains sufficient for breathing in theory, but the partial pressure of oxygen becomes so low that the lungs are no longer able to effectively saturate the blood. After a few minutes, hypoxia develops, and after 10 to 15 minutes, without special protection, the person loses consciousness. That is why all military pilots flying above a certain level use pure oxygen or an enriched gas mixture. The oxygen mask in this case is not a choice, but is an element of life support. Modern aircraft have moved beyond simply supplying oxygen. 4th and 5th generation fighters are equipped with onboard oxygen generator systems, known by the abbreviation OBOG. These installations operate without cylinders and without ground refueling. They take air from the engine compressor, pass it through a molecular filter made of zeolite sieves, and release pure oxygen during flight. At first glance, this technology seems reliable, but in history, it has already become the cause of a serious crisis. In 2010, several pilots flying a fighter jet designated Raptor reported symptoms of hypoxia in the cockpit. Dizziness, disorientation, and confusion were accompanied by the fact that one of the pilots in the air could not remember basic control procedures. According to some experts, the OBOG system at a certain moment began to supply an insufficient amount of oxygen, and according to other versions, contaminants from the engine compressor could have entered the breathing mixture. Following the incident, the Raptor fleet temporarily restricted flight altitudes, and pilots began using finger-mounted pulse oximeters to monitor blood oxygen saturation in real time. The problem was officially declared resolved, but several years later pilots noted that the symptoms persisted even after upgrading the system. There was no official clarification on the final result of the investigation. The situation highlights how vulnerable the human body is in conditions for which it was not designed. The technology compensates for the lack of oxygen, but when a failure occurs, the pilot has only a few seconds left to prevent disaster. One of the most famous weapons used on modern combat aircraft is the 8-barrel automatic cannon mount, known as the GAU-8 Avenger. The gun has a caliber of 30 millimeters and is capable of firing at a rate of fire of up to 4,000 rounds per minute. The projectile, which uses a depleted uranium core, weighs about 300 grams and accelerates to a speed of 1,000 meters per second. This configuration makes it not just a gun, but a key element explaining the existence of the heavy fighter with the designation A-10. A projectile with a uranium core differs from a conventional armor-piercing projectile in that upon impact, the uranium sharpens itself. The front part crumbles, revealing a sharp cone-shaped tip. The uranium ignites, creating a stream of hot particles inside the affected object. A tank with the designation T-72, which has frontal armor of about 500 millimeters in steel equivalent, becomes a serious target. The GAU-8 cannon hits such tanks in the roof of the turret or in the upper projection of the hull, where the armor is much thinner. This is tactic A-10, attack from above and from behind into the least protected areas. The 7 barrels are arranged in a circle and rotate in a Gatling-like pattern. Each barrel fires 1 shot per revolution, allowing time to cool while the rotor completes a full circle. With 1 barrel fixed and such a rate of fire, it would melt in seconds. The gun weighs about 280 kilograms, and its ammunition capacity is 1,175 shells. At maximum rate of fire, all ammunition can be expended in 17 seconds, but in practice, pilots fire short bursts lasting 1 to 2 seconds, firing between 60 and 120 rounds in a single pass. The recoil of the gun at full rate of fire reaches about 4 tons, which is comparable to the thrust of one of the 2 A-10 engines. When firing, the plane literally slows down, and long bursts can drown out the engines as powder gases enter the air intakes. This problem was solved by limiting the location of the air intakes and the direction of the barrels. The GAU Gun 8 dates back to an era when there were many armored vehicles on the battlefield, and the skies above remained relatively safe. Today such conditions have become rare, but the gun remains, because sometimes in battle you need a tool that works crudely, simply, and reliably. Movies often show how a plane hit by fire turns into a huge ball of fire, and a bullet piercing the fuel tank causes an instant explosion. The reality is significantly different. Aviation kerosene, known in American military aviation as JP-8, is not gasoline. Gasoline evaporates easily, and its vapors can explode from the slightest spark. Kerosene is less volatile and more similar to diesel fuel. At room temperature, a flammable match brought to the surface of a puddle of kerosene will most likely go out, and the flame will not transfer to the fuel. Kerosene requires a temperature above 55 degrees Celsius to ignite, which is its flash point. Only at this temperature does a sufficient amount of vapor form above the surface to support combustion. In a jet engine, kerosene is specially sprayed by nozzles in the form of a fine mist, which allows it to burn efficiently. Without atomization, fuel burns slowly and reluctantly. This feature played an important role in the history of aviation. During World War II, airplanes using gasoline often burst into flames when the tanks were punctured, causing severe burns to the pilots. The switch to kerosene significantly reduced the fire danger in combat conditions. Modern military aircraft further protect the fuel tanks by filling them with a neutral gas, usually nitrogen, which is located in the space above the fuel. Removing oxygen from this volume eliminates the possibility of combustion even when the fuel is heated above its flash point. In addition, the tanks are covered with a special rubber shell, which when pierced, self-tightens, closing small holes before a significant amount of fuel leaks out. Thus, aviation kerosene actually burns quietly and does not explode. The fireballs seen in the movies are a staged effect with the addition of flammable liquids that are not used in real fuel tanks. One of the key elements of modern air strategy is the Airborne Early Warning and Control Aircraft, known as the E-3 Sentry. This is the Airborne Warning and Control System, abbreviated as AWACS. On the top of the fuselage is a disc-shaped radar device with a diameter of about 9 meters, which rotates once every 10 seconds. It is capable of detecting air targets at a distance of more than 450 kilometers and simultaneously tracking hundreds of objects. This capability changes the nature of air combat. A conventional fighter aircraft sees only what its own onboard radar displays, limited by its viewing angle and range of several hundred kilometers. AWACS, in turn, provides a complete picture of the battlefield, transmitting it to all aircraft in the operation area. A fighter pilot can receive information from AWACS without turning on his own radar, thereby hiding his position from the enemy. Operators aboard AWACS manage the air battle like a chess game, directing interceptors, coordinating strikes, and warning of emerging threats. An example of the effectiveness of AWACS is the conflict in the Persian Gulf in 1991, when air systems detected all Iraqi aircraft from the moment they took off. Not a single Iraqi plane could suddenly appear in front of the American pilots, and the American planes operated with an information advantage that the enemy did not have. Information superiority in modern warfare is often more important than quantitative advantage in technology. The vulnerability of AWACS lies in its large size, slow maneuverability, and high cost. One long-range missile strike can destroy the entire air combat control system, which is why AWACS always operate under the cover of fighters and are located far from the front line. The first flight of AWACS took place in 1952, and the last aircraft of the series rolled off the assembly line in 1962. However, the Model B-52 Stratoforce continues to fly in the American military. This aircraft, designed under Stalin, remains a combat unit in the 21st century. It is a large glider with a huge payload capacity, capable of carrying a payload of about 31 tons and covering distances of more than 14,000 kilometers without refueling. The aircraft's service ceiling is 15,000 meters. The design of the airframe remains unchanged, but over 70 years the US military has constantly updated its contents without changing the shell. The engines have been changed several times, starting with 8 Pratt & Whitney J57 turbojet units, then moving to the more fuel-efficient Pratt & Whitney TF33 models, and replacement with even more modern units is currently being considered to reduce fuel consumption. Avionics have been completely modernized. Modern equipment in the cockpit has nothing in common with the original instruments. Modern navigation systems, digital sighting systems, and communication systems have completely replaced outdated analogs. The B-52's armament has also gone through several generations. Initially, the aircraft carried free-fall nuclear bombs, then moved on to cruise missiles, and later to guided bombs such as JDEM. Now the airframe is being modernized for the use of hypersonic weapons. The same aircraft, in service for 7 decades, remains relevant thanks to the constant updating of weapons and control systems. At the same time, the B-52 was never developed to break through modern air defense. It does not fly into the active countermeasures zone, but operates from a safe distance, firing missiles or guided munitions and rushing to the rear. For such a role, a large glider does not require stealth coverage or supersonic speed. As long as it has the ability to engage targets from a safe distance, it remains in demand. The US military plans to operate the B-52 until 2051 and beyond, giving the aircraft nearly 100 years of service. No other military aircraft in history has come close to this service life. This demonstrates how important flexibility and upgradability are in the long term. Night flight at low altitude requires special preparation. A speed of 500 kilometers per hour and an altitude of 30 meters above the ground create conditions under which the lack of navigation systems can lead to instant death. The modern military pilot uses several key tools to fly in the dark. The first of these is night vision devices, which magnify the residual light of stars, the moon, and distant lights tens of thousands of times, making the picture green and detailed. However, such devices narrow the field of view. Normal peripheral vision covers about 180 degrees, while a monocular night sight provides only about 40 degrees. The pilot is forced to compensate for the narrow field of view by constantly moving his head and judging distances without the usual stereoscopic perception. The second piece of night equipment is a thermal imager known as FLIR, which is a forward-facing infrared sensor. A camera installed in the nose of the aircraft or in a separate housing records the thermal radiation of living beings, operating engines, and heated surfaces. The image is displayed on the screen in the cockpit or on the helmet visor. A thermal imager reveals what a night vision device does not see. A person hidden in the bushes becomes clearly visible due to its own heat, and a car left without an engine retains a heat trace for a long time. The third component of night flight is a terrain-following navigation system known as TERNA. The radar looks forward and down, maps the terrain, and automatically adjusts the flight altitude, maintaining a given above-ground level. The pilot asks modern combat installations of the NACA and Martin Baker series are complex launch vehicles. They record the aircraft's flight vector and adjust the angle of the shot. This allows the pilot to maintain an upward trajectory relative to the Earth's surface. The systems already operate at zero speed and at zero altitude, that is, directly from the surface. Military aviation does not stand still. While you are listening to this chronicle, new projects are already being assembled in closed hangars, which we will learn about only in 20 years. These developments will once again change the rules of the game. That is why it is worth observing the development of aircraft carrier groups with special attention, because their future will determine the balance of power in the world's oceans.